Video, I'll introduce the analytic definition of a limit and run through a practice problem. The analytic definition of a limit is something more rigorous, stated in more rigorous mathematical language than the language we've been using, which is x gets close to a point and y gets close to a point and so on. So a more rigorous way to phrase this is the analytic definition. Because it is more rigorous, it is also much more difficult, and therefore most introductory calculus classes don't even talk about this. They just skip it, and a math major will typically encounter this material in a later class. But I'll go ahead and present it here. You don't need to know it, but if you are just interested in the more rigorous foundations of the subject, I present it here. So here's the definition. We define the limit of f is L at x naught. That's what we are trying to define, this phrase. What does it mean? It means that for every positive real number, epsilon, which I tend to regard as an error or a distance, and I'll talk more about that later, but generally, you want to think about epsilon as some kind of a y-coordinate, I don't know, maybe call it permittivity or something like that, that you are allowed to get it a little bit wrong on the y-axis, right? That's kind of the idea of limits approaching your limiting value, but never actually touching it. So there's this little bit of error that is permissible. And then there's, so for each epsilon, for each error bounds that you put on the limiting value, there is some corresponding error bound on the x-axis that if it's small enough, right, if your error bounds on the x-axis are small enough, then you will keep the function within these error bounds on the y-axis. So epsilon and delta are two things that I regard as error bounds, and so anyway, let's continue with the formal statement of the property, right? So L is the limit at x naught if for every error bound on the y-axis there is some error bound on the x-axis, such that being within the error bounds on the x-axis implies being within the error bounds on the y-axis. So you give me a restriction, a tight restriction on the y-axis, I can make everything fit into it by choosing an appropriate bound on the x-axis. So that's probably still very confusing. I will give an example. So for example, if f of x is x squared, and we look at the limit as x approaches 1, that tells me that x naught is equal to 1, right? The value we approach is x naught. We believe that the limiting value L is 1, so we throw these numbers and this function into the statement for the limit, and then try to establish that these formal conditions hold. If these formal conditions hold, then we know the limit exists and is equal to 1. So we suppose that we have any arbitrary epsilon. We do not know what epsilon is. It could be anything. It is our error bound on the y values. And I will start by scrutinizing this. It's usually easier to do these proofs if we start here. So if I look at what this is, I would like to phrase it in terms of something that is related to absolute x minus x naught, or in this case, x minus 1. If I could do that, then maybe it'll give me a good, easy way of choosing my delta to make everything work, right? So I assume that epsilon is anything, and my task right now is to find the corresponding delta that would make everything work. So if I substitute into this expression the f of x value, the L value, I get this. And clearly, that factors. I'm looking for my delta, so I want to phrase this in terms of something that has to do with x minus 1. Well, it factors easily, and then I can distribute the absolute value and divide by x plus 1. I now have some kind of a nice statement about absolute x minus 1 that hopefully will guide me to an easy choice of delta. Now, if I could just make delta equal to this, that would be lovely, but I can't because x is a varying quantity, right? This would not be a choice of delta that is at some specific real number upon deciding what epsilon is, right? I need to, know what epsilon is and make my choice of delta, but I can't do that here. I would have to know both epsilon and x, and that's not good enough. I need some particular number that only depends on perhaps epsilon. So how can I do this? Well, one thing I can do is I can just choose to make delta less than a half, right? I mean, if I can find delta less than a half, then I can find a delta, right? It doesn't matter that it's less than a half. So I specifically always look for a delta that is less than a half. And the reason I do that is because I know that by doing that, I force the choice of x to have a distance of 1/2 away from the number 1. That's what this expression basically can be read as, is saying that the distance from 1 is less than delta. So if I pick delta less than a half, I know that x cannot be farther away from 1 than a half. That puts x somewhere between 0.5 and 1.5. And the very valuable thing about that is that therefore absolute x plus 1 is between 3 halves and 5 halves, or between 1.5 and 2.5. I choose among that range of values, I choose the one that would guarantee epsilon over absolute x plus 1 would necessarily be greater than that, because I make that choice, right? That's the choice I make for delta. So I'm choosing delta to be this. And because I choose delta to be equal to this, I guarantee that it's less than this. Now I have exactly what I want. What did I want? I wanted to be able to say this up here, that absolute x minus 1 less than epsilon over x plus 1. If I could get this, I just sort of backtrack it to here, and I will have exactly the goal that I started out with. So by making this choice, I get that x minus 1, absolute x minus 1, is less than this, and having done so, now that I have made this choice of delta, which is this specific real number, I get this inequation, and I can backtrack it to exactly the thing that I wanted to have. This establishes that the condition for L being the limit is satisfied. Therefore, L is the limit. So there's my example, and in the next video, we'll start doing some exercises.